So I just wanted to take a few minutes to talk about the type system in Vortex and the different types that it allows you to construct and use within your programs. But I also want to touch upon generic types and how Vortex's type system actually has its own runtime. But firstly, let's just go through some examples. So I've got a couple of types over here. You've probably seen these a billion times before in other languages, but essentially the first one is an interface. So the way we'd use an interface is if we do const vec, and let's give it the type of that interface, and we'll give it an object as a value that adheres to that type. So x needs to be a number, and y needs to be a number as well. So if we go ahead and run this, we actually get a compile time error. And just quickly, the reason we get this error is because Vortex is both nominally and structurally typed. And what that means is we can't just give a random unnamed object to a value that's typed as a named type. So we have a type called vecnum. It expects the object to be initialized as a vecnum and not as a random object. And the way we fix this error is quite simple. So we just put vecnum right in front of that object. And what that is now an object initialization. And it's going to initialize this object as a vecnum. So if we go ahead and run this, everything is all good. All right, so we've seen this before. This is pretty boring stuff. The next thing here is a parametric type or a generic type. And again, we've seen these a billion times before in other languages, but the way they'd work is if we have, for example, actually let's create another type from that type, because parametric types, their whole purpose is to basically spit out a new type based on whatever parameters that we inject. So if we have, for example, let's create another type called vec I, all right? And then we basically say vec I equals vec, and we'll just give it a number. And then if we just print vec I for a second, we'll see that vec I is actually just an object that takes x and y, and they're both numbers. That's because we've given vec a number here. If we do string, then you'll see string and so on and so forth. So what we've covered here is pretty basic. It's pretty self-explanatory, and we've encountered this a billion times before in other languages. But I did want to mention this because this is where we start talking about how Vortex's type system actually works. And I'll do that with a fresh example. So as mentioned before, Vortex's type system has its own runtime. And what that means is it actually runs pieces of code. Now, it runs them in a very constrained and limited way, and it omits specific things from happening. So it doesn't allow printing to the console. It doesn't allow writing to files or creating new files, or most things that cause side effects are constrained. So they don't actually run. They're unable to run during this pre-runtime compilation stage. Just a clarification point, Vortex is an interpreted language. It's not compiled, but it's easier to say compile time than pre-runtime. So whenever I say compile time, I literally mean a stage that happens before runtime. So now that we understand that Vortex's type system has its own runtime, what does that actually allow us to do? Well, because we can run code, things like for loops, while loops, maps, object initializations, things like that can actually happen inside type construction. And I'll show you a very, very quick example of that. So if I have a type, and we'll call it blah. All right, we'll make it a generic type first, and we'll do that by passing the brackets there. Now, brackets can take things like T, K, or whatever else you want as a generic, but we'll just keep it a blank for now, and we'll give it a body. So type blah is a generic, but what I want to do here is I want to say, okay, I want to build a list from 0 to 100, and then pass that through as a type. So how do I do this? Well, let's just construct the list via a for loop. So if I do var ls, which is list equals empty list, and then we run a for loop from 0 to 100, let's say, we'll expose the index, and then we'll just append I. So ls.append I, and then we'll just return ls. So if I run this function, if I call this type, this runs that function and it creates that list at compile time and it sends it through. So if I do type some type equals blah, if I go ahead and print some type, we'll see it's an actual list that was built at compile time. So that for loop actually ran. Now, I want to actually, a slight modification to this, which might not be relevant to this video, but I want this list to actually act as a literal list, as a tuple. So I'll just do as literal over here, which doesn't really change anything if we print it out. But what this allows me to do is if I have a variable over here, so if I have a const x and I give it the type some type, and then I give it, say, a list of strings, so like 1, 2, or whatever, and I run this, I'm going to get a compile time error that says, look, x expects a value of type this whole thing because it's a literal list, which is a tuple. So we expect it to be exactly this type, but it received value of type string list. Now, the most important thing here is that this is actually a compile time error. This is not a runtime error. So I'm building this thing out at compile time, and I'm successfully using it somewhere else in the code. So this is why Vortex's type system allows you to do these things. And it does so because of that pre-runtime compilation stage that actually runs pieces of code. So I'll show you a few examples of types that I've written before and that I have used in my code base. And these are, if you're a keen observer, you'll notice that a lot of these are actually pulled directly from TypeScript. And TypeScript offers these as utility types. And I've just basically mimicked those in Vortex. But let's have a look at a few of them. Well, let's have a look at pick, for example. So what pick is, again, it's a generic type. It takes T and keys. So T is constrained to be an object. Keys is constrained to be key of that object. And then we basically run this function, which basically creates a partial object, it loops through the keys, and then it creates a partial of that key. Now, this would not be possible if Vortex didn't have a runtime at the compilation stage. But because it does, it allows you to construct objects and lists and more complex types at compile time, which I think is really cool. So another one would be emit, which basically emits specific keys from the object. Create nullable, non-nullable, intersection types, common types, exclusive, etc., etc. But I just wanted to touch on that and explain why I've chosen to implement it this way and how it can be powerful. One other thing I did want to touch on is I could actually call external libraries from within that function over here, which means it gets called at compile time. But the library itself actually has to declare that the functionality that I'm providing is pure. And what that means is it has to be tagged as pure for it to run inside the compilation stage. And I'll show you what I mean in string. So string is a library that I've implemented. And as you can see, it's actually tagged as pure. So this is just a tag. All it does is it passes a string tag to the next node in whatever it encounters. So pure here actually just passes pure to the entire library. And all that's saying is, look, I'm pure, so I can actually, you can call all of these things here safely at compile time, and there's no side effects. So that's all good. You can do that. Um, if I look at things like I/O, you'll notice that the library itself is not labeled as pure, but specific functionalities are. So write and input are not pure because they could lead to side effects. So they're not actually labeled as pure, which means when they're called at compile time, it basically just returns whatever its type is. So it returns a generic string if I call input, but it doesn't actually run the input function. Whereas things labeled as pure, for example, readf, if I want to be able to read a file at compile time, I can actually do that because it's labeled as pure. And that's kind of it, really. That's just what I wanted to clarify about the type system. Now, could it lead to dangerous code? Possibly. Could it lead to, infinite while loops, all that kind of stuff? Yes, definitely. But I think the balance here is that it provides a lot of power to build very, very complex, very, very specific types. And I think it's really quite cool. But yep, that's all I wanted to clarify. So thanks for watching.